In this lecture, we will learn about graph algorithms. We will use how randomization can help solve the all pair shortest path problem. So, the input is a graph which is an unweighted graph, and we want the output to be the shortest path between every pair of vertices. The classical algorithms for this would be the Dijkstra's algorithm, and then there is the Floyd-Warshall algorithm, and there is Johnson's algorithm. All these algorithms take proportional to n cube. So, Dijkstra can be implemented in say m times n plus n square log n time, same with Johnson's, whereas Floyd-Warshall will take n cube. Okay. So, in some sense you might feel like if the shortest path between pairs of vertices are long, then the output itself should take order n for every pair, and the n square pair, therefore, n cube is the best possible. But what we will look at is a slightly modified version, wherein we are given a succinct representation or an implicit representation of the shortest path, which would mean that given a pair of vertices, from this representation we can compute the shortest path spending time proportional to the length of the path. And if we allow for that kind of output, the question is how good can we do? Can we do better than O n cube? We will see that this can be done. We will first solve a very closely related problem, wherein you do not have to determine the exact path, but instead the length of the path would be fine. So, this problem we will call it as the all pairs distance problem. So, here the output will be for every pair I comma j, we should have a matrix such that the I jth entry of that matrix is the shortest distance from I to j, or shortest path, length of the shortest path. Okay. So, the objective is to create such a matrix. Now, this matrix, the entries are all between 1 and n, and therefore, or 0 and n minus 1, and therefore, the output need not be very large. How do we solve this problem? This is closely related to the problem of matrix multiplication. If you look at the matrix A and the matrix A square, okay, suppose A is an incidence, A is the adjacency matrix, of some graph G, then A square is basically the adjacency matrix of a graph G prime, wherein there is an edge between I and j if there is a path between I and j of distance 2. In fact, the entry will correspond to the number of such paths. So, A square we will write it as the matrix, you can think of it as a matrix whose I comma j entry tells us the number of paths of length 2 between I and j. Okay, so, suppose we could calculate A square, given A, if we could calculate all these different matrix products up to a to the power n, from these we can determine the length of the shortest path. That would basically mean that there are n matrix multiplications that you have to do, and each matrix multiplication would, if you use the naive algorithm, take n cube steps. So, n into n cube, it is much more than cubic. The question here would be, since there is some relation to matrix multiplication, can we use matrix multiplication without doing all these calculations and still come up with the all pair shortest distances? Okay. So, we will do that. Let us introduce a few terms and we will look at a square of a graph. So, let us say G is a graph and G prime is another graph which we will refer to as the square of G. Okay. So, we will define what it means to call a graph as a square of another graph. In some sense the adjacency matrix is squared, but you also allow in for paths of length 1. Okay. So, if G is the graph denoted by V comma E and let A be its adjacency matrix. Okay. And let D be its distance matrix. Okay. When we talk about the square of a graph, it means a graph which is obtained by adding all those edges such that they were either connected in G or connected by an edge, or they were connected by a path of length 2. In other words, G prime contains I comma j as an edge if there is a path in G of length at most 2. Okay. I comma I edges, we do not bother about it. Okay. So, that is our graph G prime. Now, the adjacency matrix of G prime, let us call that as A prime, and the distance matrix, let us call it as D prime. Okay. A couple of observations based on this definition. If you look at a path in G of length, let us say 100, surely G prime will contain a path between these two vertices itself of length 50. If there was a path of length 101, then G prime would contain a path of length 51. Okay. We will make these notions formal. So, let us just look at this statement. When suppose G prime is complete, okay, it is a complete graph. This will happen when is G prime a complete graph? This happens only if the diameter of G is going to be less than or equal to 2. It means every vertex was connected to another vertex by a path of length at most 2. If that is the case, then G prime is going to be complete, and that is an if and only if condition. Now, if G prime was complete, can we somehow use D prime to compute D? Okay, are they related? So, we have this particular relation D is 2 times A prime minus A, okay, when G prime is complete. Okay. So, if you know the adjacency matrix of G prime, twice that minus A would give you G. So, that is a matrix computation. Okay. So, from the distance matrix you can figure out that it is a complete graph. The square of G is a complete graph. Then from that information we can recover back the distance matrix for G by taking twice the adjacency matrix of A and subtracting A from it. This works only if the diameter is 2. For arbitrary diameter, what can we do? Okay. So, can we somehow look at the square of the graph and from the distance matrix of the square of the graph recover back the distance matrix of the graph? Okay. So, that is our objective. Recover the distance matrix of G from the distance matrix of G prime. And why are we doing this? And suppose we want to compute, I mean our objective was to compute the distance matrix of G, instead we will compute the distance matrix for G prime, okay, and that we will do recursively. At some stage the square will be the complete graph, and for the complete graph we know how to compute the distance matrix of its square root, and we can basically use that procedure to have a recursive algorithm to solve the all pair distance problem. So, this is the useful lemma that we will use. if dij is even, where dij denotes a distance between I and j in graph G. This would imply that dij is equal to 2 times d prime ij. Okay. So, d prime ij is the distance between I and j in this squared graph, and if dij is odd, this would imply that dij is equal to 2 times d prime ij minus 1. Okay. So, let us see, but this is an easy statement. Why is this true? So, let us look at any path. If this path was of length 100 and this is a path in G, automatically, so this is a path in G, you can skip one vertex when you are traversing these in G prime, okay, because there is an edge from let us say A1 to A3 and A3 to A5 and so on. Okay. So, any path of length 100 will have a corresponding path of length 50 in G prime. Okay. And if the path is of length 101, then there is surely a path of length 51 in the other graph. Okay. So, let us see a formal proof of this. We will just do one case where dij is odd. So, suppose dij is odd, so it is of the form 2l plus 1, okay. Then clearly d prime ij. So, d prime ij is the shortest path between I and j in this squared graph. That is going to be less than l plus 1, less than or equal to l plus 1, because take 2 at a time, the last edge has to be used as it is, the other ones contribute to l, last one contributes 1. So, l plus 1 is the length of the shortest path, is no more than l plus 1. If you look at the path between I and j in the graph G prime, clearly there is a path of length at most l plus 1. Can it be anything less than l plus 1? Okay. So, suppose it is l or any other number smaller, let us just take l. If it is l, then you can take such a path in G prime and convert it into a path of length at most 2l. Okay. In other words, so this is our first part, dij is less than l plus 1. The second part would be, if dij prime is less than or equal to l, then dij will be less than or equal to 2 times l, which is strictly less than 2l plus 1. But we assumed that the shortest path in G was of between I and j is of length 2l plus 1. Therefore, dij cannot be less than or equal to l. In other words, dij should be greater than l, and there is precisely one number. So, this would imply, so 1 2 would imply that d prime I j is equal to l plus 1. So, when dij is odd, the following relation holds. This would imply 2 times d prime I comma j minus 1 is equal to dij. So, what does this tell us? We have a graph whose distances we already know. For example, G prime, means the distance matrix is denoted by d prime. From d prime we can recover dij if we know the parity, the oddness and evenness of the distances. But now the question becomes, would be to determine the parity of these distances. So, if we know the parity, then we can recurse and compute all the individual distances. Okay. So, how do we compute parity? Again, the following easy lemma helps us do this. If dij is even, then dkj prime is greater than dij prime for all neighbors of I, and if Dij is odd, then dkj prime is going to be less than dij prime for all neighbors of I, and there will exist a k such that d prime kj is less than d prime ij. Okay. So, we are giving a condition by which we can ascertain whether Dij is even or odd. Okay. So, let us see why such a statement is true. So, let us first consider the case where Dij is even. The shortest path from I to j is of even length. If you look at the shortest path from k to j, so this is I and this is j. If you look at the shortest path from k to j, it is either passing through I. If it is passing through I, surely that is going to be greater than or equal to, or it is a path of odd length. Okay. So, here this is even, and k to j it passes through I. This cannot be, the k to j path cannot be of even length, because if it were of even length, then I to j shortest path would be of odd length, which contradicts our assumption that I to j shortest path was even. Okay. Suppose k to j, the shortest path was of length, say some even length. Okay. Now, this shortest path from k to j, its length is certainly less than or equal to 101, because there is surely a path of length 101. And if we additionally assume that this k to j path, shortest path, was of even length, then it can only be 90, it can be 100, or if it is 98, there is a problem, because if it is 98, then there is a path from I to j whose length is only 100. Okay. So, if the I to j path is even, that would mean that dkj for any neighbor, this is going to be greater than or equal to 99, okay, or this is going to be greater than 2l minus 1. Okay. And therefore, by the previous lemma, we can conclude that d prime kj is going to be greater than d prime ij is just going to be half. So, that is going to be 50 or L, and dkj is going to be greater than or equal to L. Okay. So, that is the proof that whenever Dij is even, there would surely be, for all neighbors of I, d prime kj is greater than or equal to Dij prime, and a similar argument works for the case where Dij is odd. When Dij is odd, you can show that d prime kj is going to be less than d prime ij for all neighbors, and there will surely be one neighbor for which this is strictly less. Okay. So, this characterizes the nature of the parity of Dij. So, we could look at neighbors in the squared graph and look at their distances, and based on whether they are greater than or less than, we can decide whether Dij is even or odd. So, we can write this as a simpler condition, a cleaner criteria. So, compute summation d prime kj, where k varies over neighbors of I. This should be greater than d times d prime ij, okay, if Dij is even, and this summation k belonging to neighbors of I, d prime kj should be strictly less than d into d prime ij if Dij is odd. So, if we wanted to know whether Dij is odd or even, we basically need to compute these quantities, that is summation k belonging to neighbors of I d prime kj, and if it is greater than the degree of I, times d prime I j, then we can conclude that it is even, otherwise we can conclude that it is odd. And this calculation, summation k belonging to neighbors of I d prime k j, can be written as a matrix multiplication. This is just product over A all k going from 1 to n A I k. Okay. So, A I k is 1 only if k is a neighbor of I times d prime k j. Okay. So, this if we call it as S I j, then we can compute these quantities. If S I j is greater than d I into d prime I j, then d I j is even, and if it is less, then d I j is odd. Okay. So, by doing one matrix multiplication, we can determine the parity of d I j. Okay. So, we can convert this into an algorithm. We will write down the algorithm. So, this is a deterministic algorithm to determine the distances. So, we will start off with the input is a graph and the output will be the distance matrix of G. Okay. So, first we will have to compute Z is equal to A square. So, this is the adjacency matrix of the graph obtained by taking where there is an edge between I and j, if and only if there is a path of length 2 between I and j. And compute A prime, the adjacency matrix of the square of G from Z and A. Okay. So, that would involve a little bit of calculation. In A prime, there is an edge between I and j if there is either a path of length 2 or a path of length 1, okay, and I is not equal to j. So, A prime can be computed, and if when A prime I j is equal to 1 for all I comma j where I is not equal to j, then d will be equal to 2 times A prime minus A. Okay, and then we will return this particular d. That is, if you have computed the adjacency matrix of the square and if it is the complete matrix, then we readily compute the distance matrix from the adjacency matrices and return that. If that is not the case, we need to recursively compute the distance matrix of A prime. So, compute the distance matrix of A prime. Okay. So, that is, let us call it as d prime and its adjacency matrix is A prime. We will compute S is equal to A times d prime. We are computing A times d prime, so that we can do this check which helps us determine whether d I j is even or odd. Okay. And from S we are going to compute d. So, d I j is equal to 2 times d prime I j. This is when d I j was even, and how do we check whether d I j is even? So, you have to look at the S I jth entry, and if that is greater than d prime I j times z I I. Z I I was the square of A. If there is a path between I and I of length 2, so the condition that we needed to check here is S I j is greater than or equal to d I times d prime I j. So, d prime I j is available here, and that multiplied by the degree. So, the degree would be just the I ith entry in the square. So, this is the number of neighbors. Okay. And this is equal to 2 times d prime I j minus 1 if S I j is less than d prime I j into Z I I. Okay. So, this is how we compute the all pair distance matrix. Okay. Now, the question becomes, if we have the all pair distance matrix, can we use that to compute the shortest path? Okay. So, that will be the next topic.